Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And welcome to my channel. In this video, we are going to discuss about traveling salesman problems, or sometimes we call it TSP. In which, in this problem, we are asked, okay, to find the shortest yet most efficient route for a person to take given a list of specific destination. Okay, in this case, so-called salesmen have to start from a particular vertex, have to go, okay, to many different vertex. In that case, maybe branches or customers, and then exactly once, and then have to return to his office or to the headquarters. But before we can explain and try to solve TSP, maybe we need to understand first what we mean by Hamiltonian circuit. So this definition of it, that is a Hamiltonian circuit begins at a vertex, maybe we call it headquarters, HQ, go through each vertex exactly once, and then return to the same vertex. Okay, that's the circuit. Okay, start at one particular vertex, go to each vertex exactly once, and then return back to the original vertex. That's what we call Hamiltonian circuit. Now, before we proceed with the traveling salesman problem, we try to understand or trying to figure out in this graph. This is what we call graph here. Now, in this graph, is there Hamiltonian circuit in this graph? Now, suppose that we start at A. Okay, this is A here. Do we have Hamiltonian circuit? So what we are asking here is that whether, okay, there is a circuit starting from A, going through every vertex and then return back to A. Now let's try, okay, trace our route here starting from this vertex. Now suppose that we go from A, we go to B. Right? We go, this is our first, okay, first we call it path, right? Okay, we take the road from A to B first, and then maybe we like to go from B. Maybe we want to go to C. That's our next destination. Okay. Now from C we cannot return. We cannot return from C to A yet because there are many more vertices that we haven't visited yet. For example, D, F, E. So we have to continue our journey from C. So from C we need to go maybe to F, right? So this is number 2, route number 2, and then this is number 3. Okay, so now we are at vertex F, and we need to go to this vertex, that is vertex D. So how to do that? Yeah, we can go this way. Okay, so that's number 4. Now from D, we need to go from D because there is one more vertex here that haven't been visited yet. That is vertex E. So we need to go from D to E, and there is no path direct from D to E. So we have to go back to F. All right. So we have maybe we use different color. Maybe we have used this one. So we go back this way. But if you do that, then that means that you have visited F has been visited twice. So that cannot be done because the definition of a Hamiltonian circuit is that we have to pass through every vertex exactly once, okay, only one time. But in this case, okay, we already passed vertex F 2 times. Therefore, we fail to get a Hamiltonian circuit if we follow this way. So maybe we can try another, what we call another route. Let's see, do it one more time. Maybe this time we'll find a Hamiltonian circuit in this graph. Okay, now we start at A again. Okay, so we start at A. Just now we go, okay, go to B first. Now let's go different way. So we go from A to C first. Okay, we go to from A to C first. And then from C, maybe we go to B. Okay, this is our path number 1. This is path number 2. Okay, we already visited C and B. Now from B, we better go to D. Alright, so from B we go to D. Yes, like this. So this is route number 3. Yes. Now where should we go from D? Yeah, of course we don't have choice. We need to go to F. We can choose that way. So this is path number 4. Now from F we can proceed to E. We can proceed to E from F. So this is our path number 5. Right? Now from E we need, okay, we already visited all the vertex. See, we already go to vertex C. B also visited already. D also already visited. F also done. Now from E we have to return to the original vertex, that is A. Okay, so this one is path number 6. So we already find, yes, this route here, that is from A to C, from C to B, from B to D, from D to F, from F to E, and from E to A, is a Hamiltonian circuit. So I can write down the route. What is the route? That is A, and then I go to C, then I go to B, then I go to D, then we go from D to F, from F we go to E, and then we go back to our original vertex, that is A. Okay, that's we call it route A, C, B, D, F, E, A, and this route is a Hamiltonian circuit. A Hamiltonian circuit. Yes, this graph has a Hamiltonian circuit. Where is it? This is the route ACB, DF, EA. Okay, now let's see another example. Okay, we are given a graph here and see whether we get a Hamiltonian circuit in this example. All right, now start at point what? Start at point E. Okay, where is E? Oh yes, E is here. We are going to start from E. Now let's go to, from E we go to D. Okay. Now from D we need to go to point or to vertex C, right? Because we have to visit every vertex. Okay, so we go from D to C. So this is our path number 1. This is path number 2. Alright. So now from C, we want to go to some other vertex, for example B. So we have to return this way. But if we do that, that means we already pass this vertex D 2 times. Okay. It shows very clearly that in this case, we don't have. In this case, okay, we don't have. Here we don't have Hamiltonian circuit. Okay, because we are going to pass point D or vertex D twice. Okay, the same thing will happen at point B here. We need to go to A, okay, and then we have to, okay, to come back using the same path from A to B. So we are going to pass through point B twice also. So for this particular circuit, there is no, for this particular graph, there is no Hamiltonian circuit. All right. Now let's see the definition of another type of graph. We call it complete graph. Okay, what we mean by complete graph, that is a graph is called complete if there is exactly one edge between every pair of vertices in the graph. Now suppose that, for example, we have three vertices. For example, we have A, we have B, we have C. Now suppose that we have uh, an edge from A to B. We have like that. And we have an edge from B to C. And also we have an edge from C to A. Now, is this graph complete? What we mean to say is there an edge from A, for example, to every other vertex? Okay, in this case, yes, because from A you can go to B, there is an edge there. From A also you can go to C, all right? So this is a complete graph, okay, when we have three vertices. Now, for example, if we have four vertices, okay, let's do that. So this is A, suppose that this is B. Now let's say this is C and this is D. Now suppose that we have graph like this. Now is this graph is complete yet? No, because there is no edge between A to C. There is no edge yet. Okay. Now how about this one? Okay, is this graph is complete? Not yet, because there is no edge between C to D. How about this one? Is this graph is complete now? Not yet, because there is no edge between A and D. I mean here direct graph. I mean direct edge from A to D. There is no such edge. So if we draw a line here like this, now let's ask ourselves: is this graph now complete? No, it's still not. It's still not complete, because there is no direct edge between A, for example, from A to C. Okay, let's do that now. From A to C, now we have a direct graph, a direct edge, I mean. So now, is this graph is complete? Not yet, because there is no line joining B and D. So if we draw this particular edge here from B to D, now is this whole thing, that is the whole graph here, is complete? Yes. Now this graph A, B, C, D is complete because there is an edge, okay, connecting between any two vertex. For example, from A to C, you have this edge. From B to D, you have this direct edge here from B to D. From A to B, you have to have this one. You see, you have an edge between any vertex. Therefore, this graph here is complete. Let's see another example of a complete graph like this. Okay, this is also an example of complete graph. Maybe we can label the vertices of this graph. For example, this A, this is B, C there. Now suppose this is D. Now let's this vertex E, and we have F there. Now, why we say that this graph is complete? Okay, because there is a direct edge every pair of vertices, okay, in this graph. For example, from A to C, do you have a direct graph? I mean direct edge? Yes. From A to C, you have this one. From B to D, yes, you have this one. How about from F to D? You have this one. Okay. Now, if we have, for example, like 1, 2, 3, 4, 5, 6, like in this case, we have 6 vertices, right? We have 6 vertices. Now, in order for this graph to be complete, okay, from each vertex there must be 5. There must be 5 edges, okay, going out from each vertex. Okay. For example, at vertex C we have 1, 2, 3, 4, 5. Okay. From vertex C we have 5 edges going out from from point or from vertex C. The same thing with D. Here we have 5. 1, 2, 3, 4, 5. Each one of these vertex, they have 5 line, 5 edges that's going out from each of these vertex. Okay, therefore that's the way to to check whether a particular graph is complete or otherwise. So this graph is complete. All right, now let's continue with another definition that we call weighted graph. Okay, this is the definition of it. A weighted graph is a graph for which a number called a weight is assigned to each edge of the graph. You see here in this particular graph, okay, for each edge we assign, okay, we write a number on each edge. For example, from A to D, okay, we have number 13. From B to C, okay, we assign number 3 there. For example, from A to C, we assign 6. Okay, for each edge there is a number assigned to it. Okay, and this number in our application problems may represent the distance, maybe from, for example, from A to D, the distance is maybe 13 kilometer. Okay, in that case, from B to D, the distance is 8, that is 8 kilometer, and so on and so forth. Maybe also these numbers represent the cost, okay, the cost of traveling from one point to the other. For example, if we travel from point A to point B, okay, the cost is 9 what? Maybe 9,000 ringgit, maybe. Maybe from A, see here, from A to C, the number is 6. If this is 9,000, so this is 6,000, and so on and so forth. So in application problem, we are going to assign numbers, okay, to each. All right. So this is what we call weighted graph. All right. So another example here, road mileage. All right. So we write this what we call this situation in a number line. Okay, we have maybe cities here, or what we call location A. This is point B. This is point C. The distance from A to B is 60 kilometer. The distance from point B to point C is 20 kilometer. Now, diagram shows the distance between three cities. Present the information using a complete weighted graph. Okay, like the previous one. Okay, like in this graph here, this is a complete graph. Okay, because there is a line or an edge that connect between any pair of vertices, and also at the same time we have numbers assigned to each edge. Therefore, this graph is complete weighted graph. So what we are going to do, okay, for this problem is we would like to have a complete weighted graph to represent this situation. So how to do that? In this case, we have only 3 vertices, right? A, B, and C. So let's draw it somewhere here. So we have point A, right? Or vertex A. We have vertex B, and we have vertex C, right? So we are given in this number line that the distance from A to B is 60. So we can draw an edge from A to B and assign a number to it, that is 60. Okay, where 60 represents 60 kilometer. From B to C, the distance is 20 kilometer. So from B to C, the distance is 20 kilometer. You see, from A to B is 60. This number here 60, and from B to C is 20. You see, when we draw a graph, okay, our drawing is not according or not following any scale. You see here the distance from this is 60, this is 20. Okay, it's supposed to be this line from B to C shorter because the value is smaller, right? But when we draw a graph, We are not considering drawing a line according to scale. No need. We are not going to follow any scale, right? So this is we already done from A to B and also from B to C. How about from A to C? What's the distance from point A to point C? Must be 60 kilometer plus 20 kilometer. That will be 80 kilometer. So from A to C will be 80 kilometer, and just write 80 only. We very seldom we write down the unit, so we just write the number. So we have 20 here, we have 60 there, and we have 80. So this is a complete weighted graph. Okay, so that's the way how to do it. Okay, now another example that we have, sometime the information given to us, okay, maybe in the form of a table like this. All right, there are 4 cities here in America, United States. We have Cleveland, we have New York, we have Philadelphia, and we have Pittsburgh. All right, so the way how to read this table is like this. For example, from Cleveland to New York is 473, maybe miles, maybe kilometer. From Cleveland to Pittsburgh is 129 kilometer, or whatever the unit is. It's not mentioned here in this particular problem. The distance from Philadelphia to Cleveland, for example, is 413, and so on and so forth. So what we are going, to do is we are going to represent, okay, this information that is given in the form of a table, okay, into a complete, okay, weighted graph. Okay, so how to do that? Yes, so we are going to transform the information from a table to a graph. Where is the graph? Here it is. So we have 4 cities, that is New York, we have Pittsburgh, we have Cleveland, and we have Philadelphia. Okay, and then we connect between each pair of the cities, and then we include also the distance, okay, between any 2 cities. For example, from New York to Cleveland is 473 kilometers. So we write down 473. Okay, where we get that? From New York and Cleveland, we can write, or we can read from the table. New York to Cleveland. All right, New York to Cleveland. Here it is 473. So New York to Cleveland 473. Okay, and we do it for each vertex, and also for each edge we assign a number to it. So this is the way how to do that, right? So the point is we want to go to every city exactly once. Okay, now suppose that the headquarters, okay, is in New York, for example. Now the question is how to go from New York to every cities exactly once with the minimum mileage. Which way you should go? Okay, from New York you should go to Cleveland first, or and then to Philadelphia, and then to Pittsburgh, and then come back to New York. Or maybe you go to from New York, go to Philadelphia first, and then go to next to Pittsburgh, from Pittsburgh to Cleveland. The question is, which way is the best way? All right, the best here means the minimum mile with the minimum mileage. So this is the problem, what we call traveling salesman problem, right? So this is two what we call algorithm that we can use to help solve traveling salesman problem. The first one is the algorithm we call the nearest neighbor algorithm, or we call it NNA. The other one, the greedy algorithm, we call it G for greedy, A for algorithm, GA. Okay, and I would like to make a note here that these are this algorithm is just an approximation when we have a result. Okay, by using any of this algorithm, it's just an approximation to the optimized value, not exactly the minimum value, but is close to the minimum value. And sometimes when we are lucky, we'll get the the minimum value, because we are looking for the minimum distance. For example, if we consider the distance between cities, or minimum cost if we considering the cost of the travels. All right. So this is the two methods that we are going to discuss in this what we call this video. But in this particular video, we are going to discuss the first one, that is the nearest neighbor algorithm, that is NNA. So this is the what we call the step that we have to follow in order for us to use the nearest neighbor algorithm. Okay, number one, we have to start at a vertex, at the vertex on which the circuit supposed to begin and end. Okay, in application problem, maybe the headquarters. Okay, where the boss there, So we start at that particular place, that vertex, and then from there go to every other vertex exactly once. Next is the nearest vertex not yet visited. If there is a tie, choose one. Okay, sometimes the distance between point A to point C, and from point A to point D, they have the same distance. So this is what we call a tie, when the value of the value at maybe two vertex, they are the same value. So choose one first, and then maybe we can compare later on. Then every time you follow an edge, you have to mark as we go along. Number three, after all vertices has been visited, we have to return to the starting vertex. That is, after we finish visiting all these different destinations, we have to come back to the headquarters, okay, to the point where we start the journey. And then at the end, we have to add the weight. If have a tie, compare and take the best results, right? Now let's see. We can start with this example to understand what is the process of solving traveling salesman problem by using nearest neighbor algorithm by looking at this example. And, right here in this case, we have three vertices, four, I mean A, B, C, and D, and for each edge they have assigned the values on each one, and we are asked to find, okay, starting from point A. Okay, and we have to find the Hamiltonian circuit. All right, and we have to follow this algorithm, nearest neighbor algorithm. Okay, now let's do our first example here. We start at point A. So what I have to do is I want to write down the route. Okay, I want to write it down, and also the width. Okay, the width. Yes. Okay, so from A, okay, since we are looking the nearest from A, the nearest vertex from A, we have 8. A to D is 8. Okay, the value is 8. From A to B is 12. From A to C is 5. Okay, therefore we have to pick the what we call the nearest distance. Therefore we choose 5. All right, so we follow from A, we go to C first. Okay, this is our number one path. So from A, okay, we go to C. So the value is 5 plus what? Okay, next. Now we are at C. From C, okay, we have to look again. The smallest value, what we have is we have 3 and also we have 2. Which one is the smallest one, the minimum, the nearest one? Of course, 2, right? So from C, we have to go to D, like this. So we have to take that path. So this is our path number 2. So from C, we go to D, C to D, and the value is 2. All right. Now from D, can we follow from D direct to A? No, cannot, because if we go from D to A, we are returning to the original vertex. Okay, we cannot do that because we haven't visited point or vertex B yet. So we have to go from D. We don't have choice. We have to go to B. So from D, we have to go to B this way. Okay, this is path number 3. So from D, we have to go to B, and the distance is 7. Okay. All right. So from B, all right, from B, we have to return to point A. Okay, so we have to go this way. Okay, we have to return to point A. That is path number 4, and the distance is 12. Okay, we start from A. Okay, we visited each vertex once, and then we already return to A again. So that's the what we call return to A, and that's the route. So A to C, A to C to B to D to B, and then back to A. The distance will be, we have to add these numbers, 5 plus 2 plus 7 plus 12. All right. So we are going to add this number. So this one is 7. This is 7. 7 plus 7, 14. And 14 plus 12 is 26. So the total distance is 26. Therefore, by using nearest neighbor algorithm, okay, we will get this route. That is, A have to go to C, then to D, then to B, and then go back to A. The total weight for that route is 26. Whatever the unit is, maybe 26 kilometer. All right, this is example number 1. I hope you understand and can follow the what we call this example. All right, now let's see example number 2 here. Example number 2. Okay, this time we are having how many vertices here? We have 1, 2, 3, 4, 5. The same, that is, we have 5 vertices also, like in this example. 1, 2, 3, 4. We have, in this first example, we have 4. But here we increase one more. Okay, we are having here 5. Okay, 5 vertices. Now the question is still the same. Find a route and its length using nearest neighbor algorithm. And we still start at A. All right. So we start from point A. This is, let's write down our route, and dia punya what we call it, the length or the width. Length also we can write the length. Length. We can write length. We can write width. Whatever. Okay. So from A we have 20. We have 11. We have 8. We have 5. Okay. Which one is the smallest one? Yeah. Which one is the smallest one? Yeah, 5. So we take this path from A to C. From A to C, this is our path number 1. So A to C, length is 5. All right. Now from C, we have 10, we have 6, and we have 4. So which one is smallest? The smallest value? Yeah, 4. So plus 4, that is this one, this way. From C, we go to E, plus 4 already. Now, we are now at vertex E. From E, we cannot go to A yet, okay, because we haven't go to D, we haven't go to B yet. So there are 2 more vertices we have to go to pass through. So from E, we can choose either 8 or 9. All right. So which one is smaller, 8 or 9? So we have to choose 8 because we are going to choose the smallest value. So we have to go this way. All right. So this one is pass. This is number 2. This is pass number 3, and the value is 8. So from E we go to B. All right. All right. So we have one more point that haven't visited yet. That is D. So we have to go from B. We have to go to D. We have to go this way. No choice. We have to go this way. Okay. This is number 4. Path number 4. Go to D. and this is 2, the value of 2. Now at the end, because now we already visited all the vertex and we have to return to point we starting with, that is point A, so we have to go back this way, go back to point A, okay, and that distance is 11, okay, and go back to point A. Okay, so the total is we have, now we have, this is 10, okay, 10, 11 plus 9 is 20, so the answer is 30. This is, okay, the total weight is equal to 30 kilometer, maybe 30 what, $30,000, 30,000 ringgit or whatever, that's the value, okay, 30. All right, this is example number 2. The route is A, C, E, B, D, A, and the length, the total length is 30. Now that's example number 2. Right, let's continue with example number 3. This is the diagram or the graph given to us like this. Okay, and again the question is still the same, that is trying to find the route and its length using the nearest neighbor algorithm. All right, let's see. Still we start at point A, here, and then, all right, and then where should we go? Okay, we have 5 there, we have 12 here, and we have 7 here, and we have 6. Which one is the smallest value? Yeah, 5. So we should go this way. All right, so let's write down the routes. Okay, from A we go to B first. The what we call the length, let's write it down somewhere here. This is 5 plus what? Now from B we have 0.4. We have 0.4 also down here, and then here we have 6.3. You see now we have 0.4 and 0.4. This is what we call a tie. All right, a tie, meaning there are two values or maybe more values the same, of the same value, for example 0.4 and 0.4, so we have to choose one of them. So let's choose this one first. Just choose one of them, doesn't matter, just choose. All right, so we go to D, then from A to B, B to D, and the distance is 0.4 plus. Now we are at vertex D now. The possibility is we can go to 7.5. Okay, the distance here is 13.5 and 12. 12 we cannot use this path yet because that's returning to the original point A. So we have, okay, to choose between 7.5 and 13.5. Of course 7.5 is smaller, so we are going to choose this way. From D we are going to go to E, okay, and the distance is 7.5. So this is 7.5. Now from point E, we have no choice, okay, but we have to go to C, okay, because any other vertex we have already visited. Now we have to go to C. We have to go from E. We have to go to C. All right. So we have to go to C, and the distance is 11.6. And then from C we have to go back to A. Okay, let's number the path 1. We have 2 there. We have 3 here. We have 4 there. And we have path number 5 over there. All right. So we have 5. We have 0.4. We have 7.5. We have 11.6, and we have to add that value that is equal to 6. Now if we had this number after C, we go back to our original vertex A, and if we add these numbers, okay, we are going to get 30.5 is the total length of that route. What is the route? A, B, D, E, C, A. That is the route, and the total length is 30.5. Okay, I hope you understand. Uh, okay, this example. But in this example, we have a tie, right? Because we already chosen this value of 0.5, that is this h from B to D. Now, whenever we have tie like that, we have to do one more. Okay, we have to find one more Hamiltonian circuit by using the other value, I mean, the other h from B to E. Okay, so let's do it one more time. But in this, okay, in this case, we have to find, instead of using from B to D, we are going to choose the h from B to E. Okay, the same value of for 0.4. Now let's do it one more time, and then at the end we are going to compare the value, the total length. Okay, which one is the smallest, because we are interested in finding the smallest length. All right, so again, we are going to solve the same problem but using different 0.4, different h, I mean. So we still going from A to B. So this is our root, this is our total length, this is the length. Root from A, and then from A to B, that is 5. Now from B we are not going to D because we already chosen that root. Now we have a tie here. From B we choose another one, that is from B we go to E. That is, we go through this one. Yes, we go. This is path number 1. This is path number 2. From B we go to E, and that is 0.4. All right. Now at E we can here's 7.5. We have 7, and we cannot go from E to A yet because that's returning to the original vertex, so we cannot follow from E to A yet. So from E to C we have 11.6, so we have two choice, either 7.5 or 11.6. So we choose the minimum one, that is 7.5. So from E we are going to choose from E to D this way. All right, that's our number 3. Plus 7.5, that is from E we go to D. All right, now here we are at D. Now we are at point D. Okay, we cannot use 12 because that's returning to A. Okay, we have only one choice. Okay, see here, we already visited all these different points except C yet. So D, I mean C, from D we have to go back to go to C. So we have to choose this way. From D to C. All right, that is 13.5. From D we have to go to C, and then from C we have to go back to A. So from this is number 3, this is number 4, and this is number 5. So after that we have to add with 6. Now from C we have to go back to A. Okay, this is the root, and this is the length, and the total length this time is equal to, if we add them together, we'll get 32.4. 32.4, the total length. Now if we compare, all right, tie number 1, where is it? Tie number 1, yeah, here it is. Tie number 1, the total length is 30.5. Now for tie number 2, the total length is 32.4. We are looking for the minimum total length. All right, so which route should we choose? This one, that is from tie number 2, or we choose this one, that is from tie number 1? Yeah, of course we choose from tie number 1 because the value here is less than if we compare to the value in tie number 2. All right, so as the conclusion, we are going, okay, let's write down the conclusion here. Okay, we are going to choose these routes. What I mean is this particular route, because the value that we got here, 30.5, is smaller than we get from the second tie here, 32.4. Okay, I hope you understand how to do it how to find the root. I mean, when we have a tie like that. So we have to do 2 tie or maybe 3 tie, and then compare which one is the smallest one and choose the smallest value of the total length. All right, now we have another example, that is example number 4. This time we have 6 vertices, that is A, B, C, D, and E, F, and we like to find what is the minimum total length. All right, in this graph by using nearest neighbor algorithm, and we still want to start from point A. This is our starting point. Okay, so so let's write down the what we call the root and also the total length. Okay. So we have 29, we have 25, we have 24, we have 13. Of course, the smallest one will be 13. That is from A to C. From A, go to C first. So we go from A to C this way. All right, this is root number 1. Okay, from C, we have 36, we have 10, we have 32, we have 7. Seems like 7 is the smallest value, so we have to go to this way. So from C, we have to go to E plus 7. Now from E, we have 23, we have 20, we have 38. Seems like 20 is the smallest value, so we have to go this way. Okay, from E to D, that is plus 20. Now we are at point D. Okay, we have 22 here. Okay, we cannot go back to A yet, so we have 22. And we have 4. So we have the minimum value from D is going to F. So from D to F, and the distance is only 4. Now, we already visited all the vertices except B. So we have to go from F. We have no other choice. We have to go to B. All right. So this number 1, this number 2, number 3. We have here number 4, and this is our path number 5. Okay, that is from F to B. F to B, and the distance is 31 plus 31. All right, let's move it a little bit. Okay, from B, we have to go back. We have to go back to A. This is number 6. Path number 6. So from B, we have to go back to A, and the distance is plus 29. All right, so the total length, if we add these numbers correctly, we should get 100 and 104. That's the total distance for this particular route. Okay, by using nearest neighbor algorithm, we get the route A, C, E, D, F, B, A with the total length 100, 100 and 104. Okay, now let's see our last example here. This is a little bit different if we compare to the previous one. The example says this: a delivery man at point P, where is point P? Oh yeah, this is point P there, must deliver pizza to customers A, B, C, and D. This is A there, B, okay, customer B is there, C there, and D down here. Okay, he must deliver pizza to all these customers. He start at point P. All right, maybe that's the pizza there, the pizza, what we call shop there. Visit each delivery location exactly once and then return to P. Okay, find a route and its length using nearest neighbor algorithm. Now, the thing is that for this particular example, we don't have graph yet. So what we have to have is, we have to convert this situation into a graph. Now the question is, how many how many vertex that we have? Can you tell me how many vertex we have? Yeah, of course, 5. That is, we have P, we have A, we have B, we have C, and we have D. Now let's draw the graph first. So we have 5 of them. So suppose that this is P there, this is A here, this is maybe here, maybe here C, and maybe here D. You know, the graph you can draw as you like it, as long as we have 5 points, okay, or 5 vertex, and they are complete graph and weighted graph. Now, okay, because there is a distance, each one of these is one block. We call it block. From A to C, for example, how many blocks? One. From A to C, 1, 2, 3. 3 blocks. All right. Now, each one of these, we can connect. Okay, because there is a road between A to B, or any pair of vertices. They have a road connecting between them. So let's draw what we call complete graph. All right. So we have like this. We have like this. We have this. We have this. All right. So, and also we have this. Now, from each vertex, there must be 4 edges, okay, going out from it. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Okay, we have each, okay, for each vertex, they have 4 edges going out from it. Now, let's write down the distance between, for example, P to A. Now, let's write down and count how many blocks from P to A. Okay, count how many blocks. 1, 2, 3, 4, 5, 6. So P to A, 6. So write down the weight is 6 from P to A. P to D, okay, D is over down here. So from P you move down. 1, 2, 3, 4. So P to D, the distance is 4. From A to B, 1, 2. So from A to B, only 2 blocks. Okay, we are counting blocks now. From A to C, 1, 2, 3. A to C, only 3. Okay, let's write it down there. Now, from B to C, 1, 2, 3, 4, 5. B to C, 5. B to C here, 5. D to C, we don't have yet. Okay, D to C, 1, 2, 3, 4, 5, 6, 7. D to C, 7. Okay. A to D. A to D. Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A to D, we have 10. Okay, what else? From B to D. B to D. Oh, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, B to D, 12. B to D, here we have 12. Now, how about P to B? Okay, P to B, P to B, okay. 1, 2, 3, 4, 5, 6, 7, 8. P to B, we have 8. Now, anything else? Anything else? I think already complete. Assign the width, okay, to each edge. All right, now we are ready to, okay, to find the root and its length by using nearest neighbor algorithm. Starting from P, okay, this is our point of origin here, that is P. We are starting from P and then going to every vertex exactly once and then coming back to point P. All right. So we are going to write down the what we call the root, and also we want to find the length of this root, and we are going to add them up. So we are starting from P. Yes, P. Now we have, now we have one more what we call weight that is not written yet. P to C. Now let's go back from P to C. P to C. 1, 2, 3, 4, 5. P to C 5. So I'm going to write P to C 5 like that. Sorry about that. Okay. Now we have 4. Okay. We have 5. We have 8. We have 6. 4, 5, 8, 6. Which one is the smallest one? Yeah. 4 is the smallest one. So I'm going to follow this way. Alright. So from P, I'm going to D first. P to D. PD. So 4 plus. Now from D, I have 7, I have 12, and I have 10. So the smallest one is 7. So from D, we have to go to C. Okay, this is number 1. This is number 2. So plus 7. From D, I have to go to C. Okay, plus. Now we are at C. We have 5. Okay, we have 3 there. Okay, we have only 2 choice. That is 3 or 5. So I choose 3 because 3 is smaller than 5. So choose this way. Go to A. Go to A and the distance is 3. Now, I cannot go back to P yet because we have one more point to go here. We have point B, so we don't have choice. Okay, from A, we have to go to B. From A, we have to go to B. And the distance this way is 2, plus 2. And then from B, we have to go back because we already visited all location. So we have to go back from B to our original place, that is P. We have to go that way. So from B to P. And the distance is plus 8. Okay. So now we are going to add these numbers and see what is our total length. Okay, if we add this number, we have 10 there. We have 10 also here. So 10 plus 10, 20. And 20 plus 4, this is equal to 24. Alright. So, and the root is P, D, C, A, B, P. So, the delivery man, okay, starting from P, have to go to D, and then have to go to C, go to B, to A, then go to B, and then coming back to point B. Okay. Return to the original place. And the total length, if we follow that route, is 24, maybe 24 miles, maybe 24 kilometers. Okay, that's the way how to solve traveling salesman problem by using nearest neighbor algorithm. Okay, so that's all for now. Hope you to see you again next time. Wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh.